All right, so we said vapor pressure is the pressure of the gas above a liquid, and the more gas there is, the more vapor pressure there is. So let's think about what the relationship between vapor pressure and temperature is going to be. What's going to happen to vapor pressure when we increase temperature? Well, if you think about what happens when you heat a liquid, eventually it'll start to boil, right? You're inserting more energy, you're giving more energy to break the intermolecular forces, you're causing more of those molecules to become gas. More gas molecules, more vapor pressure. So as temperatures increase, vapor pressure increased. And so that's shown in this picture right here. Come on. On the bottom here, we have temperature increasing, and we see what happens when temperature increases. This x-axis goes up, vapor pressure also goes up. And then eventually you hit the boiling point, or in this case, the normal boiling point. So let's think about what boiling is. So the boiling point occurs when the vapor pressure is equal to the atmospheric pressure. Basically, the scenario you have here is that you have your liquid trying to turn into a gas, so it's pushing up. Draw a little picture of this. Right? It's trying to turn into a gas, it's pushing up, but then you have the atmosphere pushing down. And so once these two are equal, or this liquid vapor pressure is slightly higher, it overcomes the atmospheric pressure and is allowed to boil. And so the key word here, normal boiling point, is the boiling point at 1 atmosphere. So things will boil at different temperatures depending on the atmospheric pressure. And so this is often shown in terms of the boiling point elevation of water, right, for cooking. If you are in high altitude, your food will take longer to cook, and this is the reason why. So you can see here different spots on the Earth. Mount Everest, very high. Water boils at a low 78 because the atmospheric pressure is very low. Whereas something at sea level, right, the atmospheric pressure is approximately 1 atmosphere, and so the boiling point is about 100 degrees Celsius, right? And so this explains why when you're higher up, right, maybe you're going to like Colorado mountains or something, there's a lower atmospheric pressure, which means that water boils at a lower temperature. Which means that your food takes longer to cook. Cool. So the relationship between vapor pressure and temperature is described by an equation. So vapor pressure and temperature relationship is described by the clasius clapyreon equation. I have no idea if I'm saying that pronounced, or if I'm pronouncing that correctly or not. Doesn't matter. It relates vapor pressure and temperature. The equation is pressure is equal to A, which is just a constant, E to the negative delta H of vaporization divided by RT, where R is your gas constant and T is your temperature. Sometimes you'll see that form. The more popular form is this one down here. And it says the natural log of pressure at time 2 over pressure at time 1 is equal to the delta H of vaporization of R over 1 over T1 minus 1 over T2. Sometimes you'll see different forms. You'll see P1 over P2, and then maybe there's a negative in front of the natural log. And sometimes you'll see the T1 and T2 flipped as well. There's multiple ways to correctly write the equation, and as long as you plug it in correctly, you'll get to the right answer. So just some things. R is your gas constant, but you want to talk about in terms of energy. So it's the 8.314 joules per mole Kelvin. And then the other thing you want to pay attention to is that these temperatures must be in Kelvin. You cannot have these in degrees Celsius. And so oftentimes you'll see plug and chug type of problems. So for example, if the vapor pressure at 34.0 degrees Celsius is 10.0 kilopascals, and at 98.8 degrees Celsius, it is 100.0 kilopascals. What is the enthalpy of vaporization, the delta H of vaporization? And so what you're going to do here is just plug and chug. So you have your equation, P2 over P1 equals delta H of vaporization over R times 1 over T1 minus 1 over T2. And what we want to solve for here is delta H of vaporization. So what we're going to do is we're going to multiply both sides by R. And then, or before or after that, it doesn't really matter. We're going to divide both sides by 1 over T1 minus 1 over T2 to isolate our delta H of vaporization. So then it's going to be R times the ln of P2 over P1 divided by 1 over T1 minus 1 over T2. And then at this point, we can just go ahead and plug and chug straight in, right? This is the 8.314. R is going to be the 8.314. Your P1 and your P2 are going to be these pressures, right? So if we identify this one as, we'll go with that one as P1. We'll plug that into there. That means this 100 is then the P2. Plug that into there. And then we could call this guy right here T1, but we have to be careful. You have to change it to Kelvin. So you have to add 273 to this. So it'll end up being 307 Kelvin. So we can go ahead, take this 307 Kelvin, plug it into this T1. And then this 98.8 can become our T2. Again, we have to change it to Kelvin. This will be 372 Kelvin or something very similar. And then we can plug it into here. And then after that, all you have to do is just plug it into your calculator. It doesn't matter what you pick as your P1 or P2, you just have to be consistent. So if you pick this as your P1, make sure the other one is your T1. And then if the other one's the P2, the other temperature has to be the T2. If you struggle with the math here, let me know and we can kind of work together to figure out the shortcomings, but I won't show you all the kind of algebra here. I already did all the algebra. At this point is just plug it into your calculator. And so what you'll end up with is 33,800 kilojoules per mole. So I won't have too many plug and chug problems like this, but be comfortable with them in case they show up.